In this video for Chapter 8, we're looking at what are called indeterminate forms, which are resolved by what's known as L'Hopital's rule. So let's take a look at a problem we encountered way back early in Calculus 1. Limit as x goes to 3 of x squared minus 9 over x minus 3. And the way we did this was to factor the numerator, and then we could cancel out the problem factor in the denominator, the x minus 3 that was going to 0, and we got the limit as x goes to 3 of x plus 3, and we got an answer of 6. And so this wasn't a difficult problem to do, and this method was fine. But in general, if we have a problem of this type where we have the limit as x goes to a of f of x over g of x equals 0 in the top divided by 0 in the bottom, it turns out that there's another way to find an integral like this. So let's look at a very sort of a brief proof of this, or a partial proof of it. If we have limit as x goes to a of f of x over g of x, and we know that a and f of a and g of a are both 0, and so is the limit as x goes to a, then this would be the same as the limit as x goes to a of f of x minus f of a, because f of a is 0, divided by g of x minus g of a, because g of a is 0. And so then what we're going to do next is divide the numerator and denominator by the same thing, and that is going to be x minus a, so it's f of x minus f of a over x minus a, divided by g of x minus g of a over x minus a. And we learned back in the third section of the chapter that as x goes to a, this becomes f prime of a, and this denominator becomes g prime of a, or it goes to g prime of a. It's actually the definition of g prime of a. And so that tells us that this limit is f prime of a over g prime of a. And this proof that we just went through is given the name L'Hopital's rule, even though the Frenchman L'Hopital didn't prove it, as noted in the book. It was probably one of the Bernoullis that proved it. So how would that have applied to this problem that we started off with? Limit as x approaches 3 of x squared minus 9 over x minus 3 was a 0 over 0 type limit. So the rule says, well, just take the derivative of the top and divide that by the derivative of the bottom, and then start over to take the limit as you go to the same quantity, and you see that you get the same result as we got before much more easily. We don't do this rule just because it gives us results more easily. We do it because it allows us to find limits for a much broader array of functions. So let's take another example that we looked at or verified earlier in the text, and it took us quite a few steps to do it. But with using L'Hopital's rule, it's very easy to do. So we want the limit as x goes to 0 of sine x over x. That is a 0 over 0 limit. So L'Hopital's rule says that should be the same as the limit as x goes to 0 of the derivative of the top, which is cosine x, divided by the derivative of the bottom, which is 1. We go back, see if we can take that limit. Yes, cosine of 0 is 1. The denominator is 1. And so we have the result that we obtained back in the derivative chapter much more quickly. It turns out that L'Hopital's rule can be used Actually, let's do one more example before we shift to other variations of this. So this would be the second example from page 183 is one where we need to apply L'Hopital's rule more than once. So we got limit as x goes to 0 of e to the x minus x minus 1 over x squared. We plug in 0 for x and we get 1 minus 0 minus 1 over 0, which is a 0 over 0 limit. So L'Hopital's rule says, well, it should be the same as the limit, or is the same as the limit as x goes to 0 of the derivative of the top, which is e to the x minus 1 over 2x. We let x go to 0 in the top and the bottom again, and we still get 0 over 0. It's actually 1 minus 1 over 0, but it's still 0 over 0. So we say, okay, well, can we apply L'Hopital's rule again? Yes, we can. The derivative of the top is e to the x, the derivative of the bottom is 2. We let x go to 0, the top goes to 1 because it's e to the 0, the bottom does not change, and so we get the result of this limit 1/2. And if you graph this function, you'll see that that is what it goes to as x goes to 0. L'Hopital's rule also applies just by taking reciprocals. Not only is it the case that the limit as x goes to a of f of x over f over g of x equals f prime of a, or equals, excuse me, the limit as x goes to a of f prime of x over g prime of x, if f of a and g of a over 0. It's also true if limit as x goes to a of f of x equals limit as x goes to a of g of x, if it equals 0 or plus or minus infinity. And so if we look at this third example with the infinity type, where we've got the let's look at it on the next blackboard, the limit as x goes to 0 from the right of e to the 1 over x divided by ln of x. If we let x go to 0, the top is e to the infinity, which is infinity, and the bottom is ln of infinity, which is also infinity, and so it is an infinity over infinity type. That says we can apply L'Hopital's rule to it, take the derivative of the top, and we get the same exponential times the derivative of its exponent divided by the derivative of the bottom, which upon simplification gives us the limit as x goes to 0 plus of minus e to the 1 over x over x. We let x go to 0, and we see that the top is e to the 1 over 0. Let's put it down here, e to the 1 over 0, and the bottom is just 0, but e to the 1 over 0 is e to the infinity divided by 0, so it's actually there's a minus sign out here, so it's minus infinity over 0, and so it's minus infinity is the limit of this problem. L'Hopital's rule applies to other limits than 0 over 0, and infinity over infinity. It applies to limits that can be turned into 0 over 0 or infinity over infinity. This one is actually one of the type 1 to the infinity, and it is this problem. The limit as x goes to infinity of 1 plus 1 over x to the x. This is a limit we proved back in Calculus 1 that you may remember, but let's go ahead and do it. So the way we do this problem, as we said, it's as x goes to infinity, we get 1 plus 0 to the infinity. The way to do the problem is to set it equal to y and then take ln of both sides of the problem. So ln of y equals ln of the limit as x goes to infinity of 1 plus 1 over x to the x. We use the ln property that ln of m to the r is r ln m to bring that power x out front, and so this is the same as so we brought that power x down in front, and that gives us x times ln of 1 over x limit as x goes to infinity of that. Well, as x goes to infinity, this factor right here is infinity. This factor right here becomes ln of 1 plus 0, so ln of 1, which is 0. And it turns out that certain cases of infinity times 0 can be turned into, or almost all of them actually, can be turned into either 0 over 0 or infinity over infinity. So let's see how. So we've got limit as x goes to infinity, x times ln of 1 plus 1 over x, and that is the same, algebraically the same, as the ln of 1 plus 1 over x divided by 1 over x. And so when we take the limit of the top and the bottom, the limit as x goes to infinity, this becomes ln of 1, which is 0, and the bottom is 1 over infinity, which is 0. So it's a 0 over 0 limit. We apply L'Hopital's rule. It becomes limit as x goes to infinity of the derivative of the top, which is 1 over 1 plus 1 over x, times the derivative of the inside, which is minus 1 over x squared, and then we're dividing by the derivative of the bottom, which is also minus 1 over x squared. And so we see that this and this cancel out, and we are left with the limit as x goes to infinity of ln of 1 plus 1 over x, which becomes the limit, or which actually just becomes ln of 1, which is, excuse me here, so this, there's no ln in front of this term, so this right here should just be limit as x goes to infinity of 1 plus 1 over x, and that is just 1. But remember, this whole expression was a y that we started out with, which was ln of the right-hand side, right? We took ln of y, I'm sorry, this is ln of y that we have here. So ln of y equals 1, and we make both sides powers of e, and we see that y equals e. And you may have remembered from the start of the problem that this limit right here, this limit right here is one of our definitions of e. So we've verified that that limit is e. Let's apply L'Hopital's rule to one more problem. Example 5 on page 184, and that is the limit as x goes to 0 of tangent x to the x, and tangent x to the x. So as x goes 0, tangent x goes to 0, and so it's a 0 over 0 type limit. We're going to also set this equal to y and take ln on both sides, and so that brings the power down in front, so it's x times, or it's a limit as x goes to 0 of x times ln of tangent, and we write that in the, which is a 0 times ln of 0, 0 times infinity, which we rewrite as before, ln of tangent over 1 over x. We take the derivative of the top and the bottom because this is an infinity over infinity problem, so L'Hopital's rule applies, and it becomes 1 over tangent times the derivative of tangent, which is secant squared x, and then divided by the derivative of the bottom, picking that up on the next blackboard, secant squared x over tangent x, and we had minus 1 over x squared on the bottom, which is same as minus x squared on the top, minus x squared times 1 over cosine squared x, and tangent is divided by tangent makes this cosine x over tangent x. So what are we left with here? Minus x squared divided by cosine x sine x. Question is, are we getting anywhere? Well, let's see. Does L'Hopital's rule still apply? The top goes to 0, the bottom is cosine times sine, but sine goes to 0, so it's 0 over 0. So we'll apply L'Hopital's rule once more. Derivative of the top is minus 2x. The derivative of the bottom is, let's use the simplification the book has done for us, or that's done for us in the book. Cosine squared x minus sine squared x, so the bottom just becomes cosine of 2x, and at that point we can resolve the limit because it's no longer a 0 over 0 or infinity. Or infinity, the top goes to 0, the bottom goes to 1, and so the answer is 0. Okay, and then one final example that is an infinity minus infinity type problem. So this is example 6 on page 185. The limit as x goes to 1 from the right of 1 over ln x minus 1 over x minus 1. If we plug in the 1, we get 1 over ln of 1, which is 1 over 0, and so this is infinity, and this is 1 over 0, and so it is infinity. So it is of the infinity minus infinity form. And so what do we do with that? Well, we get a common denominator. That common denominator is the product of the two denominators, so it's ln of x times x minus 1, and then the 1 here changes to x minus 1, and this 1 changes to ln x, and it is the limit as x goes to 1 of that. So let's see what we get. So it is what, 1 minus 1 minus 0, which is 0 in the top, and the bottom is ln of 1, which is 0 and times 0. So it's a 0 over 0 limit, and so L'Hopital's rule applies. So we take the derivative of the top, and we get what? 1 minus 1 over x. This is limit as x goes to 1. The derivative of the bottom is the product rule. So it's ln x times the derivative of x minus 1, which is just ln x, and then plus the derivative of ln x times x minus 1. And let's see what we have here as we let x go to 1. We still have 0 over 0, so let's resolve this. The numerator can be rewritten as x minus 1 over x if we get a common denominator, and the denominator can be written as ln of x plus so we turn it into this form by taking this x in the denominator here and dividing through by it, and so since we haven't changed it, still on the 0 over 0 form, we can apply L'Hopital's rule again. Limit as x goes to 1. Derivative of the top is 1. The derivative of the bottom by the product rule, we get what? X times 1 over x. Product rule applied to the first term here, and then plus ln x plus the derivative of x is 1. And what happens if we let x go to 1 now? In the top we get 1, and in the bottom this term is a 1, and this term is a 0, and this term is a 1, and so we've got 1/2, and we finally get a result. So here are 6 L'Hopital's rule problems that we've done, and we've done all of the variety of them. The first one that we did was a 0 over 0 problem, and then we did another 0 over 0 problem, sine x over x. Then we did one more 0 over 0 problem, this e to the x problem. We did an infinity over infinity problem, which turned out to have an answer of infinity, but wouldn't necessarily be that. It could be any number. We did a 1 to the infinity problem by taking ln on both sides. We did a 0 to the 0. This problem right here, by the way, was just e, right? An alternate version of e, as we found out. Here we did a 0 to the 0 problem, which turned out to be 0. And finally we did an infinity minus infinity problem by getting a common denominator, which turned out to have a result of 1/2. So this completes this video on section 6 of chapter 8, which we need to be able to work problems in the last section of chapter 8, as well as some of the problems in chapter 9.